I have an important announcement for you. The MMCM Civil Engineering students have just launched their very own Bahay ni Kuya. Exciting, right? Hello Philippines and hello world! Welcome to this special episode of Pinoy Big Brother Geotechnical Engineering Edition. I'm Kate Lorraine Viñega, and joining us today are our housemates, each playing the role of geotechnical engineers as they explore and experience what it takes to succeed in this field.
Lahat tayo'y mayroong pag-iba. Sa tingin pa lang ay makikita na iba't ibang kagustuhan, ngunit isang patutunguhan. Kapay at mahal ang hanap mo, magbibigay ng halaga sa'yo.
Housemates, welcome to my house. As future engineers, it is important for you to understand geotechnical engineering. This branch of civil engineering deals with the behavior of earth materials. Through centuries, this discipline evolved, giving rise to modern methods and technologies we use today.
Early foundations. In 1776, Charles Augustin de Coulomb introduced his theory on earth pressure and slope stability, explaining that the sheer strength of soils comes from both cohesion and friction. He also developed the wedge theory, the first systematic method for calculating lateral earth pressures on retaining structures. This theory remains influential, and it is still used in modified forms by engineers today. In 1887, William John Rankine expanded on Coulomb's work by applying continuum mechanics to soil stresses. He formulated equations for active and passive earth pressures and introduced simplified conditions for slope stability. In the 1920s to 40s, Carl Terzaghi, known as the father of soil mechanics, revolutionized geotechnical engineering by introducing the principle of effective stress. Through his books and theoretical soil mechanics, he provided tools to analyze consolidation and bearing capacity. Standardization of soil testing. In the early 1900s, Albert Atterberg introduced soil consistency limits to classify fine-grade soils based on their plasticity. Later, Arthur Casagrande improved on soil testing by creating the Casagrande Cup for liquid limits and creating a chart. Growth of institutions and global collaborations. In 1936, the first international conference on soil mechanics was held at Harvard, led by Carl Terzaghi and Arthur Casagrande. This event marked the start of geotechnical engineering as a global field and led to the creation of the International Society of Soil Mechanics and Geotechnical Engineering, which promotes worldwide research and knowledge sharing. Advances in slope stability, foundations, and geosynthetics. From the 1950s to 80s, geotechnical engineering made big improvements. Alan Bishop refined slope stability analysis, Ralph Peck introduced the observational method for safer designs, and geosynthetics like geotextiles and geomembranes were developed. In 1983, the International Geosynthetics Society were formed to support these innovations.
Let us not also forget that the Philippines has played a role in the development of geotechnical engineering. Filipino experts like Dr. Salvador F. Reyes advanced soil mechanics education, research and practice, while organizations such as PSS, MGE, and PICE provided platforms for Filipino engineers to engage globally and strengthen the field locally. Their efforts in consultancy, training, and collaboration contributed greatly to foundation and slope design as well as solving soil-related challenges in the country.
Housemates, your task is to find one hidden project with paper clues around the school that applies the principles of geotechnical engineering. You must determine which projects succeeded and which ones failed. Afterwards, 2 of you will be evicted. Are we clear? Alright, so ready, set, go!
This is mine. You have to find another one.
Housemates, please will proceed to the confession room. I have reviewed your tasks. 3 of you succeeded and 2 failed. Sorry, Abdel and Klein, you are now evicted since the projects you found did not succeed.
I hear myself breathing, hanging by a thread. My heart is barely beating. I haven't
Rion Antero Bridge, also called the Harius Trikopis Bridge, connects the towns of Rion and Antero in Greece. It is one of the longest cable-stayed bridges in the world and is also the longest fully suspended bridge of its kind. But what makes it special is not just its size, but where it was built. Engineers used a unique foundation design. Instead of pushing piles deep into the seabed, which would not work in soft soil, they placed huge concrete bases on top of a thick layer of gravel. The gravel layer helps spread the weight evenly and works like a cushion when the ground moves. This gives the bridge both strength and flexibility. Construction started in 1998 and was completed in 2004, just before the Athens Olympic Games. Today, the Rion Antero Bridge is seen as a masterpiece of engineering. It shows how geotechnical solutions like special foundations and earthquake-resistant systems make it possible to build safely even in one of the most difficult environments.
The Panama Canal is one of the most important waterways in the world. It connects the Atlantic and Pacific Oceans that gives ships a shortcut that saves thousands of kilometers of travel. As ships became bigger and heavier, many of them could no longer fit through its old locks. That's why the Panama Canal expansion project was launched. After nearly 10 years of work, it was completed in 2016. The expansion included a brand new set of locks, wider and deeper channels, and systems that use less water. The goal was to welcome the world's largest ships, known as New Panamax vessels, and secure Panama's place as a leader in a world trade. This project represents a significant milestone in global commerce and engineering. By increasing its capacity, the project has enhanced international trade efficiency and reinforced Panama's strategic role in connecting world economies.
Construction of Pisa began in 1173. Modern geotechnical investigation analyzed the soil, bearing capacity, and settlement. Engineers applied stabilization strategies and soil extractions, counterweights, and anchors, gradually reducing the tilt while preserving the tower of integrity. Today, the Leaning Tower of Pisa stands not only as a symbol of Italian heritage but also a remarkable case study in geotechnical engineering, showing how soil and structure interact and how science can preserve history.
The Nicol Highway collapse in Singapore on April 20, 2004 was one of the country's worst construction disasters. The failure occurred during the excavation for the Circle Line MRT tunnel works. Investigations revealed that the main cause was a design miscalculation in the retaining wall support system.
I want to talk about the Cherry Hills subdivision landslide, which happened on August 3, 1999 in Antipolo, Rizal. It was a tragedy that claimed about the lives of about 60 people and buried 378 homes. After Typhoon Ising brought heavy rain, so the soil simply became too heavy and gave way, triggering the landslide. It turned out the developers, Philippine-Japan Solidarity Corporation,
had cut corners and didn't even bother with the proper soil tests. They completely skipped the basic geotechnical and staple stability analysis. Things any good engineer would know are essential. To make things worse, nearby quarrying had left a 20-foot hanging wall that made the whole site even more unstable. The subdivision's foundations and earthworks were too flimsy to handle the saturated ground, a clear sign of shoddy engineering. This tragedy could have been avoided with a proper geological survey and a good drainage system, but it seems those were probably skipped to cut costs. In the end, the Cherry Hills disaster is a harsh lesson in why we need to take geotechnical surveys and safety standards seriously. It's a stark reminder of the massive loss of property and lives that can happen when developers prioritize profit over people.
The Cherry Hills Subdivision Landslide Initiative involved a mandatory geohazard assessment to evaluate slope stability before construction. This assessment informed the development of drainage systems and reinforcement strategies to manage water flow and reduce landslide risk. Additionally, ongoing government regulation and monitoring ensured compliance with building regulations, enhancing safety for residents. The Nicole Highway collapse highlighted the need for stronger support systems, better soil assessment, and stricter safety monitoring. Engineers reinforced trailer connections to handle soil pressures, conducted detailed analysis of soft clay behavior to reduce ground movement risk. Additionally, implemented regular inspections with real-time monitoring to detect and prevent potential construction problems.
Housemates, take note that geotechnical engineering is the foundation of every successful structure. Without understanding soil and earth materials, even the grandest buildings can collapse.
Geotechnical engineering may not always be visible, but it is everywhere beneath our feet. It is the silent force that allows skyscrapers to rise tall, bridges to span rivers, and communities to thrive on stable ground. Without careful study of soil and rock, the structures we depend on each day would face hidden risk, settlement, cracks, or even collapse. This field reminds us that the strength of any project does not begin with steel or concrete, but with the foundation of the earth itself. Through site investigations, slope stability studies, and foundation design, geotechnical engineers safeguard lives while shaping the future of infrastructures.
And that concludes our My Big Brother Geotechnical Engineering edition. Thank you, housemates, for sharing your knowledge, and thank you, class, for joining us. Until next time!